Good morning, class. Welcome to the online classes for physics of class 12th. In the previous sessions, we have been gone through the chapter that is magnetism and the matter. Today, we are going to see a revision for the whole chapter that is magnetism, which is a part of magnet and its effect. Okay. So, what all the topics that we have seen in it say. First thing, that is magnets and magnetism. We have seen that magnet is a material which have the property of attracting some materials, and this property of attraction is said to be magnetism. And we know that the materials or an objects which are showing this property of magnetism or get attracted by the magnet are said to be the magnetic substance, and the substance which are showing this property, that is they are attracting the other objects, are said to be the magnets. If we know that this magnetism word came from the place that is named as Magnesia, which is an island of Greece, right? And there we have seen that whenever the shepherds used to go for grazing their ships, they have a small iron nails in their shoes which used to get attracted. And what they came to know that at the down of that land some magnetic ores are present, that is a natural magnetic ore, due to which the shoes, or we can say that the stick which are having with them, are used to get attracted towards that land. So from there they came to know that the magnetic ores have the property of attraction. So this attracting property, from there they got the name that is magnet. Okay. And we have seen that this was the place where first time we got about the natural magnets that are having their magnetism naturally. They are naturally occurring iron ores. We can say that it as magnetite, or we can say them as lodestone also. Okay. And after that we have seen that the magnets which are showing this magnetic property by naturally, or the substance which are getting from the earth, are said to be the natural magnets. And after that we have seen that we used to get the artificial magnets also, which will be of some regular shapes. That is, whatever we want, that what shape we want, we can make it with the help of some substance. These pieces which are acquiring the property of the natural magnet and can be changed into the magnet are said to be the artificial magnet. And the advantage of these artificial magnet is that we can just make a required shape and size, that is the convenient shapes we can make of it, and we can use them. So these are more stronger than that of the natural magnets. So we can say that the natural magnets are weaker due to their inconvenient shape and size, and the natural magnets have less magnetism as compared to that of the artificial magnets. So artificial magnets can be made of convenient shapes and the sizes, and they can be of different size and shapes, like bar magnet, horseshoe magnet, or a needle that we use in a compass also, and ball-ended magnets are also there. So this type of different magnets we have seen. After that, what are the properties of the magnet? We know that the main property of the magnet is the attractive and the repulsive property. That is, whenever the object comes in contact with the magnet, they get attracted by the magnets. Okay, so this is what the first property of the magnet, that is they used to attract. Okay, so they used to attract some substance only, because we have already learned about the matters that are having some magnetism. They show different kinds of magnetism. So they are magnetic materials like paramagnetic material, diamagnetic, and ferromagnetic also. There we have seen that this attraction property somewhat change. So magnet attracts not all the kinds of the substance, but there will be some magnetism. So this property of attracting the other object is said to be the attractive property. And we also know that whenever a magnet is suspended freely, it align itself according to the geographical north and the south direction of the earth. So what we can say that there will be some two poles of the magnet which will be showing or aligning itself in the direction of the north and the south pole of the geographical, that is the earth's north and the south. Okay, north and the south of the earth's magnetic field. So this is what that we use in the compass also, that the needle used to align itself in the direction of the north and the south. So it is a directive property of the magnet. Similarly, we know that there will be two poles, at the north and the south pole. From there we can say that the ends of the magnet will have the highest strength, that is the magnetism is highest at this ends. These ends are said to be the poles, and these are named as one as a north pole and the other one will be as a south pole. So these two poles have some properties, like whenever we take two magnets with the same poles near to each other, if we are taking them near to each other, what we see that same poles will repel each other. They will never try to come near, they will oppose each other in the different directions. They will never try to come near to each other. Similarly, when we take the different poles together, that is when we keep this different poles north or the south together, then they will try to attract each other. From here what we can say that the like poles of the magnets shows the attractive property, that is they attract each other, and the unlike poles will unlike poles will attract each other, and the like poles, that is north or the south will repel each other. Okay, and we have seen that the poles, that is north and the south, will always exist in the pair, because whenever we break a magnet, then also we can't think that the north will come in one end and the other magnet will get only the south. But after breaking it also, they will get their own north and the south poles in their two pieces of the magnet also. Another two pieces also we can break, that is into the four pieces. Then also every four pieces will have their each pair of the poles. So these poles will have their individual existence. So what we can say that the magnetic poles always exist in pairs after their breakage also. Okay, so we can say that the magnet cannot be monopole, that is one pole cannot exist. There will be always dipoles, that is north and the south poles will be there. And what we know about magnetic induction, that we know that whenever a substance which can shows or which can get affected by the magnetism of the magnet, if they are kept near, then they can induce that object to be also as a magnet. Like a soft iron pieces or the iron, we know that whenever these are kept near the magnet for a long time, then what will happen, that this will try to make themselves also as a magnet. That is, whenever soft iron bar, whenever this are kept near the poles of the magnet what it will do, that it will try to attract and will try to induce this magnetism in that object also. So this induction of the magnet and the different magnetic substance placed near the poles of the magnet property is said to be the magnetic induction. Okay, and we also have seen some magnetism definitions, like this was the properties that we have now discussed, that the magnet has the attractive and the repulsive property. They have two poles, they cannot be exist as a monopole. We have seen of the magnetic lines of forces, that always the magnetic lines of forces are found in the closed curve, that is they starts from the north to the south direction outside the magnet, and it comes inside the magnet that moves from south to the north pole. So continuous they will flow, they never have a breakage, and there will be a closed circular loop will form. So magnetic field lines are a closed circular loop. Similarly, we have seen that monopole cannot exist. There will be every time the magnet, if it is breaked also, they will have their own dipoles. We have seen that the like poles repel each other, and the unlike poles, that is north and the south, will attract each other. And we have seen that if the magnet is just suspended freely through any object by a string, then it will always align itself parallel to that direction of the geographical north or the south or the Earth's magnetic field. So these are the properties. And the magnetic lines of forces, field lines, we have seen that it always forms in the closed curved loop, and it will move from north to south direction. Again it will move from the south to north direction inside the magnet. And what are the things which we have seen also, that the magnetic field, what is magnetic field? That it is the space around a magnet which can influence, or the object can be experienced by that magnet. So it is the magnetic field A, that is a space around a magnet. Similarly, we have seen uniform magnetic field. It is shown with the help of the parallel lines, that is uniform magnetic field. Equidistant parallel lines will be shown, that this will be the magnetic field lines which are shown with the letter B, that is this uniform magnetic field. Equidistant parallel lines will be used. Similarly, if the uniform magnetic field lines are just acting perpendicular to the paper and they are directed outward direction, they are directed in the outward direction, and they are represented with the help of a dot. They are represented with the help of a dot. That is, whenever a thumb, when we take and we keep it in a perpendicular direction and coming in the outward direction, then we just see a dot of the thumb. That's why it is shown with the help of a dot. Similarly, when the magnetic field acting perpendicular to the plane of the paper but directed inwards, then it is shown with the help of the cross sign. That is, whenever we take a plane of paper and we try to insert our finger, or with a pen or anything you can take, if we take it in the inward direction, that what happens, then some cross sign present over there can be seen. Like if we have in our hand also, it just gets diverted inside. So what we can say, that it is directing inside with a small cross sign. So that is shown with the help of a cross product. And what we have seen, that the magnet, in a magnet, there will be at the ends, the strength will be more. That is, if it is north and the south, these ends are said to be the poles, because at this end the magnetic strength is maximum. So this is what the magnetic poles. There are two poles which are said to be the north and the south poles, which are at the ends of the magnet. Okay, and these are inside the magnet, not at the end, but this will be inside, not at all the end, not at the end, but it will be inside the magnet itself. What is magnetic axis? That is a line which is passing through these poles will be said as a magnetic axis. If we talk about a perpendicular line to this magnetic axis at a 90 degree, then it will be said as a magnetic equator. It will be magnetic equator. Okay, and after that we have seen what the magnetic length is. That is the geographical length. What is the length of the magnet? There is geometrical length which can be taken from the center also or by the sides also. So magnetic length upon the geometrical length will be taken as its magnetic length. And we have seen the Coulomb's law also, that is force is always the product of the mass between them and inversely proportional to the distance square between them. This we have know about the Coulomb's law, but if we talk about the electric force, then we have taken the product of the charges and the inversely proportional to the distance between them. If we talk about a magnetic force, then it will be depending on the pole strength, that is the product of the pole strength or the magnetic poles, and inversely proportional to the distance between them, that is Q1 Q2 upon R square. And we know that a constant term that is given by K Q1 Q2 upon R square. This we have seen in the electric field. And if we talk about here, then it will be Q M1 M2 upon R square, that is pole strength upon distance between them. So this K will be magnetic permeability, which was given by mu naught upon 4 pi, that is equals to 10 to the power minus 7. The value of mu naught upon 4 pi is 10 to the power minus 7. And what we have seen, the magnetic dipole, that is, if we consider an arrangement of two equal poles separated by small distance, then it is said to be the magnetic dipole. Okay, and what the dipole moment is? Dipole moment is a product of either of its dipole strength, that is pole strength. It can be of north or the south, because both the pole strength will be same. So any of the strength of the magnet, its product to the geometrical length or the magnetic length, that is 2L, will be equal to that of the dipole moment. And dipole moment is given by M, which is equals to the pole strength into 2L. Okay, and what we have seen, that this magnetic field can be found due to this bar magnet at any point, and this can be seen with the help of axial position and the equatorial position, which you have seen in the electric field also. So what we have seen, that whenever a point is taken at P, which is at the axial position to that of the magnet, and if you take a point P which is at the equatorial or the point on the equator, will be taken as equatorial position. And what we have seen, that the point P, the bar or the force experienced on that point due to that of the bar magnet's north pole, and again we will find that the force experienced by that particle on the point P due to the south pole. So both the pole strength we will be taking, and we know that the force will be given by the either of the pole strength and inversely proportional to that of the distance between them. If we talk about the point on the P, then from the north pole it will be R minus L, because the distance taken from the pole's corner, that is from the south pole to that of the point P, it will be R plus L, and from the north pole or the center it will be R minus L, because from the center the point P is taken at the distance R, and from the center the pole's length will be taken as L. So together it will be 2L, that is the magnetic length. But if we take about the point P, then it will be R minus L and one will be R plus L. So on solving this, what we will get, that the force experienced by, that is the axial position, the total magnetic field at the point P, that is taken as the force experienced by the unit north pole and due to the south pole also. So what it will be, that is Fn minus Fs. Resultant force will be Fn minus Fs. It will be mu naught upon 4 pi. If we take out the pole strength, then it will be 1 upon R minus L whole square minus 1 upon R plus whole square. On solving this, we get 4RL upon R square minus L square. If we take that the length of the magnet, or we take a short bar magnet, then what it will be, that the magnetic field length, that is we are finding the point P, then the length of that point P from the magnet will be larger than that of the value of the length of the bar magnet. So L will be much smaller than that of the R. So L will be neglected and R will be taken, that is R cube will be remaining, and we know that 4RL and 2L into M will be taken as 2M and R will be cancelled out, so it will be equal to 2M upon R cube. Similarly, we have seen in the electric field also, that is 2P upon R cube for the axial position, and for the equatorial position it is P upon R cube. Here also we are taking a point P which is at a equatorial position from the point P, which is a distance R from the point from the center of the magnet, and the hypotenuse distance will be R square plus L square under root. Okay, so here also we will finding the net force by taking the both the subtraction of it, then it will be taken as mu naught upon 4 pi m R square plus L square to the power 3 by 2. Similarly, we will take that the magnet length can be smaller than that of the distance of that point from the poles of the magnet. So here also the point will be m upon R cube, because equatorial position it will be m upon R cube, and for axial position it will be 2m upon R cube. Now we will see that the torque on the magnetic dipole in the magnetic field. If we take a bar magnet of length 2L in the uniform magnetic field, and if it had taken angle theta, that it is kept at with angle inclined with an angle of theta with the magnetic field B, that is uniform magnetic field, which is shown with the equidistant parallel lines. So if we take this magnet to be kept in the uniform magnetic field, then it will try to move, that is it will try to align itself in the direction parallel to that of the magnetic field. So what we can say that there will be the two couple of forces acting on it, which both of it will be trying to move it in the parallel direction, and this force will be equal to that of the couple of force. So this couple of force is said to be torque. So what we can say, that torque will be acting on the magnet to make it parallel to the magnetic field B. And so whenever this torque act, which will be equal to the force and the perpendicular distance through which it have to move, so will be equal to that of the product of force acting on it and the perpendicular distance between it. So what the force will be, because for electric we have it written as QE, that is the force experienced by a unit charge. So it was given by QE. Here it will be QB, because magnetic field is acting, so it will be QB, and QB will be given as Q into B, that is pole strength into magnetic field. And the perpendicular distance you can see here, that is 2L is the magnetic length, so 2L sin theta will be its perpendicular distance. So on multiplying QMB into 2L sin theta, so Q into 2L will be the magnetic dipole moment, which is given by M. So it will be MB sin theta, or M cross B also can be seen. So what we can say, that if the theta is 0 degree, sin 0 will be 0, so tau will also be 0, that is torque will be 0. So if the magnetic is having it, or we can say that it is not inclined, it will be in the direction parallel to that of the magnetic field. So there is no need to movement, right? So there is no need to move, because it is already aligned itself in the parallel direction. So no need to make it in the direction parallel to that of the magnetic field. So the value of theta will be 0. So what we can say, that the force of value to move it in the direction parallel to magnetic field will also be 0. So the value of the torque will be minimum for that point when the theta is 0. And if the magnetic will be lying perpendicular to the direction of the magnetic field, that is the theta will be 90 degree, then what we can say, the maximum torque will be required to make it in the direction of the parallel magnetic field, because if we take it with theta inclined with 60 degree or 30 degree, so the force will be of half, or we can say that some force will be required but of less quantity than of the perpendicular, because it is, if it is taken as perpendicular, so 90 degree difference between that of the magnetic field and the torque, that is the length of the magnet. So what we can say, that the maximum force will be required in theta equals to 90 degree, because at theta 90 sin theta will be 1, so it will be m cross b into 1, that is mb. It will depend on the magnetic strength also and the magnetic field also. So theta, if it is taken as 90 degree, or the magnet is kept at perpendicular to the direction of the magnetic field, then the torque acting on it will be the maximum. And what we have talked about, the potential energy, then the work stored of rotating a magnet, or the torque acting on the magnet, can be stored as a potential energy. So what this work done can be given as, that is the force acting on it, that is torque, and how much it is displaced, that is with an angle d theta. So it will be equal to tau d theta, which is equal to mb sin theta d theta. And on integrating, what we can find out, dw will be integrated by the limit 0 to w, and if sine theta, it will be integrated from theta 1 to theta 2. So what we can say that as, that is mb, and sine theta d theta will be integrated and we will get minus cos theta. So on taking this, we can say that potential energy U will be equals to minus mb cos theta, and torque was given by mb sin theta. So if we take theta equals to 0 degree, then cos 0 will be 1, so maximum potential energy will be the, and if we take as theta is equals to 90 degrees, so cos 90 will be 0, so this is the minimum, and if it is taken as 180, then the positive, or we can say potential energy of the maximum, it is anti-parallel. We can say that the magnetic energy is anti-parallel to that of the magnetic field. Okay. So this was the point, and similarly we have seen that the magnet field lines were like this, that is moving from north to south. If we take our iron springs on that magnet, then we can see that magnetic field lines are arranged such that it can be moving from north to south, and inside the magnet it is moving from south to north. And what else we have seen? This were the magnet and its properties, torque, potential energy, and we have seen the dipole moment of a revolving electron. If we talk about a dipole moment, we know that whenever the magnet is taken as the arrangement with two different poles with a distance between them with a 2L, then the product of these two will be taken as the dipole moment. We know that whenever an electron, it always revolves around the nucleus and in a circular orbit. So electron revolves around the positively charged nucleus, and this electron is equivalent to a current loop, because we know that whenever we take a circular current loop, then the force was given by, or the magnetic field given by mu naught upon 4 pi I upon 2I upon r, right, for the center. Similarly, it will depend on the current and the area of that loop. So what we can say that here, similarly, these electrons moving in the nucleus will also be depending on the magnetic dipole moment, that is equal to the current and the area of that circular orbit. Okay, so what we can say that the current will be of same value that the charge taken by the per unit time. So it will be equal to 2 pi r nu. So from there we can say that the Bohr's magnetron also come, that's the orbital magnetic moment can be given as E nu r upon 2. Okay, so from here you can find out the value of the hydrogen's Bohr quantization, that is EH upon 4 pi me, where it is orbital magnetic moment for an electron revolving around the nucleus. After that, we have seen for the Earth's magnetic field, because we know that Earth behaves itself as a magnet, it will be equivalent to that of a bar magnet present on this horizontal point, that is Earth's magnetic field. So what are the things that we have seen in the Earth's magnetic field? It also have the same poles like a magnet or a artificial magnet have, like north and the south. Similarly, we can find here also, that is the Earth's magnetic field will have some points, like it is taken by magnetic equator, magnetic axis, magnetic meridian, and the geographical meridian. So what are the points? We can see in the figure also, this magnet, if we consider a bar magnet in the middle of the equator through the Earth, then it is what the point is, that is the axis passing through the magnetic north and the south pole of the Earth, it is called magnetic axis. Similarly, magnetic equator, that is a perpendicular line that is passing through the magnetic axis, is said to be the magnetic equator, that is the equator of the Earth. Similarly, geographical north and the south is there. So Earth's magnetic north pole and Earth's magnetic south pole will be there, and this geographical north and the south can be seen. So the vertical line passing through the magnetic axis suspended small magnet is called magnetic meridian. That is, we can say that the vertical line passing through the magnetic axis. So vertical line passing through it will be given as the magnetic meridian. And what is geographical meridian? The vertical line passing through the geographical north and the south. So magnetic axis perpendicular line or the vertical plane passing through the magnetic axis will be magnetic meridian, and the vertical plane passing through the geographical north and the south will be taken as geographical meridian. And what else we have seen, that the angle of declination and the angle of dip. Angle of declination was the angle between the geographical meridian and the magnetic meridian, that is the angle from the north south axis, and the angle, that is the vertical plane passing through the magnetic axis. So angle between both this axis will be taken as the angle of declination. Similarly, angle of dip was the angle between the total Earth's magnetic field B with the horizontal direction of the magnetic meridian is called the angle of depth. Okay. So here we are going to some magnetic materials and their important terms, that is magnetizing field. If we talk about the magnetizing field, what it was, that is the space around the magnet. Magnetic field was given as space around the magnet which is taken as a, or the body can be influenced by that magnet, is given as magnetic field. And if we talk about magnetizing field, then it is given as that when a magnetic material is placed in the magnetic field, we consider that if a magnetic material kept in a magnetic field, then the magnetism is induced in that. So the magnetic field that exists in that induces magnetism. So the field which is inducing this magnetism is said to be the magnetizing field, and this magnetizing field is given by B, which will depend on the number of the turns and the current flowing through it, that is equals to mu naught n I. So the field is called magnetizing field caused by the current in the solenoid. If we talk about the solenoid, there, because moving charges also produces magnetism, so from there we can say it as. Okay. Similarly, if we talk about the magnetic induction, we already say that any magnetic material kept near the magnetic pole, then it induces magnetic induction, that is B naught, which will depend on the Earth's magnetism, that is the magnetic induction, mu naught, that is given by magnetic permeability and number of turns for the solenoid or the toroid. And if we talk about I, then the magnetization of the current, that is surface current, how much it is having, the term which is induced by the current. So total magnetic field inside a magnetic material can be given as the magnetizing field and the magnetic field produced due to the magnetization. So magnetic induction can be defined as the total number of magnetic lines of force passing through them normally, and it is given by the letter T Tesla itself, because the unit will be the same, because magnetic lines of force will be given as the number of the magnetic lines of force passing normally to that of the material, so it will be given as B itself, that is given by the Tesla. Okay. And magnetizing field intensity, that is how much you are going to induce it, that is magnetic field intensity is different, intensity of magnetization is also different. So the ability of magnetizing a material is said to be the magnetizing field intensity, how much it can, you can say that induce of material, that is how much a material can be induced by the magnetism. So intensity of magnetization, that how much the body can be induced by that magnet, or the power of the magnet, and how much it can induce, it is given by intensity of magnetization, that is magnetic movement developed in 1 unit of volume by the material used in a magnetizing field, because magnetizing field will allow the body to be get magnetized. So how much it is going to magnetize, that will depend on the field, that is the magnetizing field intensity, that is H, which will depend on the number of turns current, that is given by H is equals to B naught upon mu naught. Similarly, intensity of magnetization, that how much power it will get induced by that magnetism or the field of magnetizing, that is given by magnetic moment developed per unit volume. It is given by the letter capital M, which is equals to small m upon B. And we also seen magnetic permeability, that is mu is equals to B upon H, because now only we have seen that B is equals to H upon H into mu naught, that is given by, or H is equals to B naught upon mu. From there we can find out mu is equals to B upon H. So permeability is defined as the ratio of the magnetic induction to the magnetic field intensity, that is H. Relative permeability can be given as mu r, mu upon mu naught, that is mediums to that of the permeability of the free space. Magnetic susceptibility, defined as the ratio of the intensity of the magnetization to that of the magnetic field intensity, that is the ability of a substance to take up a magnetization, that how much it can take up the magnetization, that is given for the susceptibility chi. It is denoted by the letter chi, which is equals to magnetizing field intensity H and the magnetic or the intensity of the magnetization M. So what is the relationship between this? So you can write it as magnetic permeability mu r is equals to 1 plus chi m. Similarly, B is equals to mu naught H plus N also. So what we have seen after this, that the classification of the magnetic materials, that the materials which can get magnetized by the magnet when they are kept in the magnetic field, they were of three types, that is diamagnetic substance, paramagnetic substance and ferromagnetic substance. Other than this, two more magnetic substances are there, that is ferrimagnetism and antiferromagnetism also. So what were the diamagnetic substance? The substance would get feebly magnetized by the magnet and they get aligned themselves in the direction parallel to that of the, but in the opposite direction to that of the magnetic field. They get feebly magnetized and they are repelled by the magnet, but always move from the stronger part to that of the weaker part also, but in the direction opposite to the direction of the magnetic field. Similarly, if we talk about a paramagnetic substance, then it will get feebly magnetized but in the direction of the magnetic field, and this moves from the weaker part to that of the stronger part. Okay. So we can say that the behavior of the diamagnetic substance is independent of the temperature, because when increasing the temperature also it cannot get magnetized by the magnet and it will always repelled by the magnet. So the substance which get repelled by the magnet are taken as a diamagnetic substance like gold, copper, bismuth, lead, zinc, etc. And paramagnetic substance which get attracted, but they get feebly attracted in the direction of the magnetic field. That will take time, but with increasing temperature will try to align themselves in the direction of the magnetic field, that it will get parallel to that of the direction of the magnetic field. So what it will be like, at very high magnetic fields, and it will require a very less temperature, that is at very less temperature itself it will get magnetized in the direction of the magnetic field. So this atomic dipole moments, they will try to align themselves in the direction, and the point where they get align themselves and get into the direction of the magnetic field is said to be the saturation magnetization value, that is MS. Okay. So it is independent, not, but it will depend on the temperature, and here the diamagnetic substance will be independent of the temperature. And for example, it will be manganese, aluminium, chromium, but it will be feebly magnetized by the magnet and will small, easily not attracted by the magnet, but it will show some magnetism, at a feeble magnetism. Similarly, ferromagnetic materials are those which will show the strong magnetization in the direction of the magnetizing field, and they get easily attracted by the magnet and they try to move from the weaker to stronger part very easily, and very fastly they move from weaker to the stronger part, that is like soft iron or like alnico or iron, cobalt, nickel. Many examples are there for which get magnetized easily by the magnet. If we talk about a Curie's law, then we know that far away from the saturation, the body, whenever the temperature increases, it shows this magnetization, and we know that the magnetic susceptibility, that is given for the ability of a substance to take up the magnetization when it is kept in the magnetizing field. So susceptibility of the material can be given as the Curie's temperature and its ratio to that of the temperature T, that is Curie's constant C and the temperature T. So what it is, that is directly proportional to the H and inversely proportional to the temperature, because it requires a very high magnetic field but requires a very low temperature. Similarly, from there Curie's law come, Curie's constant also come, that is C, and if you take out the value of C, then it will be m upon h into T. So this m upon h will become chi and it will be C upon T, that is directly proportional to that of the Curie's constant, inversely proportional to the temperature. So from the graph you can see here that intensity of a magnetization and the m, that is magnetized intensity, that is m upon h or h upon t. So if you take this m and h upon t's graph, then what it will happen, that Curie's law reason is there, that whenever the temperature increases, the point will come where the saturation magnetization value will come. Similarly, for the ferromagnetism, along with the Curie waves also come, that is given by Curie's waves law. Here the displacement is there in the atomic dipoles of the substance, but they try to align themselves in the parallel to that of the direction of the magnetic field. Okay, so here the temperature is not required. It is given by the Curie waves law, that is chi m is equals to C upon T minus Tc. That is the susceptibility of the ferromagnetic above the Curie temperature is inversely proportional to the temperature, because here the less magnetic external magnetic field is required but temperature is high. Okay. Now we have seen about the properties also, that whenever it is kept in the direction of the magnetic field, it get feebly attracted or feebly repelled by the magnet, and if you take it in the direction of the magnetic field, it get feebly attracted, and the ferromagnetic substance get easily attracted. So we have seen different examples also, and we have seen differentiate between this diamagnetic, paramagnetic, ferromagnetic substance also. On that basis, we have seen the hysteresis loop also, that the ferromagnetic substance, after removing that external magnetic field also, but they will have some residual magnetism in it, which this curve shows that they have some residual magnetism, that is retentivity is given by the curve of the graph. And if we take out that also, it cannot come to the initial point of the magnetization, so external force is more required to change it into the initial point. So to make it zero, what you can say, the external force is required. This force is given as the coercive force, and the point is said to be coercivity. So the loop again it will go to the point where it cannot change again into the, or not more than, the induction will not show, it will be the saturation point. So positive saturation is also there and the negative saturation is also there. So retentivity and coercivity as shown in the graph, because the body is always that paramagnetic substance, the body is always having some residual magnetism in it. Unless that coercivity or the coercive force is applied in it, cannot come to the initial position. So this lagging of the magnetic induction behind the magnetizing field is called the hysteresis, and the loop which is came from this graph is said to be the hysteresis loop. Okay. So this were the topics which we have seen, and we have seen about the magnetometers, galvanometer, electromagnets, and the methods of making the permanent magnet also, that is by holding the steel rod in the north-south direction or keeping the two magnets together. Because transformer cores are also used, that is of high initial permeability, low hysteresis loss should be there, no resistivity should be there. And similarly, for making the electromagnet, high initial permeability should be there. Those are the magnetization should be large even for a small magnetizing field. That is, magnetizing field will be small, but the magnetization for that small field also should be very large. And low retentivity, that is, if the switch is off, the magnetizing current should also lost. There should not be any residual magnetism. Okay, permanent magnet, then it should be high retentivity and should have the high coercivity also, and high permeability also required. And after that we have seen the tangent galvanometer, which works on the tangent law, that is, if two magnetic fields are taken perpendicular to each other, then the resultant magnetism can be seen with an angle theta of it, which is given as B upon BH, which is equal to the tan theta. That is, tangent law is taken as B is equals to BH tan theta. With the help of this galvanometer, we can find the magnetic moment also. So this is for the tangent galvanometer. It is having 3 circular loops. It is a device which measures a very small current. It have a moving magnet also, and it have a small aluminum coil. When the compass comes near to it, the magnet comes near to it, it get deflected. And here the 3 terminals were also given, which depend on the number of the turns and get connected to it, that is 250 and the 500 turns of the insulated copper wire. And the ends of the coils are connected to the 3 base terminals. And you can say that the circular frame of a non-magnetic material is also mounted. That the non-magnetic material, we can say it as ebonite, which is used for making the keys also. In the lab you may have seen the 2-way or the 1-way key. That black material is used, it is the ebonite, that is the non-magnetic material. So tangent galvanometer, it is leveled out and it gets parallel to the length of the magnetic needle. From there we can find out the magnetic field also. Okay. Similarly, we have seen the some mathematical derivation also, that the magnetic field at the center of the coil will be that of the mu naught I upon 2r. From there we can say that it depends on the number of turns, current, and its radius. So radius of the coil also. From there we have seen that the reduction factor also comes, that is the tangent galvanometer's constant also. After that we have seen that the oscillation of a freely suspended magnet, because we know that whenever a magnet is suspended freely, then it just try to align itself in the direction parallel to that of the magnetic field, and the couple of forces acted on it, which is given by QB. Then the couple of forces is said to be the torque, and torque was given as MB sin theta, that is M cross B is given. Since it is restoring itself, so it is a restoring torque which is in the negative direction, so minus MB cos theta will be given. If we take a small angular displacement not theta, and sin theta will be that of similar to theta, then it is tau MB theta. And if we take this tau as I alpha, that is acting on it in a moment of inertia, that is half mr square, and alpha, that is the angular acceleration acting on that body, I alpha will be equal to that of alpha can be given as d omega by dt, that is angular velocity, and again the omega can be given as d theta by dt. So alpha can be given as d square theta by dt square. So this is what the deflection, that is due to the moment of inertia and the deflecting torque. So what we can say, the deflecting torque should be similar to that of the restoring torque, because it is trying to align itself in the direction parallel to that of the magnetic field. So I d square theta by dt square will be equal to that of minus mb theta. From there we can find out the value that d square theta by dt square, that is alpha, will be proportional to that of the angular displacement theta or the angular velocity omega. So from there we can say that the oscillation used to be done for a magnet when it is freely suspended in the uniform magnetic field, and it moves and two couple of forces acts on it, so it just possesses a simple harmonic motion. So from there we can find out the time of oscillation also, that is 2 pi upon omega, or omega is equals to 2 pi by t. From there if I put out the value of omega, that is m into b, so that value is already kept here, that is mb upon I is equals to alpha. So from there we have put the value, that is omega is equals to under root mb upon I. So it just reverse because omega is in the denominator, so it will be I upon mb. So after that we have seen the vibrational magnetometer, that is a device which is covered by a wooden box, and it have a glass covers which is used to compare the magnetic moment of two different magnets, and it can compare the magnetic moment of the Earth's magnetic field also, and it can compare the magnetic moment of same length magnet also and different length of the magnets also, same size and same mass magnet also it can measure, and it can measure two different mass and the same size magnet also. Okay, so we have seen that galvanometer also, that it is a wooden shape and it have a string through which a magnet is just kept or suspended, and the reference line was there, and a mirror is also at the down, and at that reference line we have to put a different magnet, and similarly and that suspension we can put the two different length of the magnets on each other, that inclined on each other. By saying that we can find out the comparison of the magnetic moments of that two different unequal sizes and the masses of the magnet, that we have seen that m2 upon m1 was given by t2 square minus t1 square also, and we can compare the horizontal component of the Earth's magnetic field also. So these were the topics which we have seen in this chapter, that is magnetism. So from tomorrow onwards we will be going to start the new chapter, that is electromagnetic induction and its effect, that alternating current will also come. So electromagnetic induction will be seen in the next class. So thank you class. You can see the whole chapter together in this video. So try to see it and complete your topics fastly. Thank you.